All right, Math 6620, methods of reduction, transitioning into factor analysis and principal component analysis. Um, two things that are really important sometimes in education research. I'll tell you in complete transparency, I created this video previously and it went on for about 55 minutes, way too long, and most of it was me just rambling on about stuff that didn't need to be shared. So the purpose of this video is to collapse it from 55 minutes down to about 12 to 15, which would be accomplished if I would quit rambling. So let's get to it. So let's say that we are, well, the first thing we need to do is we need to think about the difference between observed variables and latent variables. So observed variables are things that we can measure that have been observed, some sort of maybe academic performance, maybe the ACT, SAT, some state score. That would be an observed performance measure, something that we could observe and measure. But sometimes there are these underlying characteristics that we can't uh, directly observe. I think of maybe self-esteem, intelligence, a lot of emphasis these days on predicting success in online courses by something we call a grit. Now we can't just say personality. Also would be something else just came to my mind. We can't just ask someone, well, what is your personality? What we would do is we would ask a set of questions similar to what I have on the screen in the left white box. And then if I dive into analyzing my data, I'm going to see that a lot of these questions are actually highly related and quote unquote load on a particular component or factor. So that's what we would have here. So I would say that the first question in general, how would you say your health is? And I'm kind of circling it right there, would load on a um, uh, kind of a latent variable, if you will, of kind of a physical well-being. Contrast that with something down here. Are you happy at school? Well, that may be a question that would quote unquote load on, a feeling of in a school environment. So again, before we get into the nuts and bolts of this, it's important that we um, know the difference between something that is observed and measurable and something that is a latent variable that's kind of lurking around there and it's quote unquote measuring something but not directly. And again, anxiety, intelligence, self-esteem, grit, perseverance, personality are examples of those things. Now, example number two, a director of a graduate program, maybe me, is interested in the set of student characteristics used to predict success. Well, certain things that I can observe would be your performance in college, a GRE score, and other things that I've listed there. Now, first gen college student, that's actually one um, variable that I've never looked at. But I have at the undergraduate level, but I've never looked at it at the graduate level. These latent, non-observed variables may be personality, motivation, intellect, grit, things of that nature. So why do we study this? Well, first of all, we've studied previously in regression techniques that multicollinearity can cause major issues with our model design. It can inflate the standard errors. It causes unstable and unreliable estimated regression coefficients. Um, so what we see there is, as I said, personality measure may highly correlate with some measure of motivation and academic history. Well, if we're trying to include personality, motivation, academic history in a model and they highly correlate, then I have multicollinearity issues and I'm forced to pick one over the other. Well, if I do that, if I eliminate predictors, I'm going to explain less variance. If I create composite scores, I'm going to explain less variance. But if I create principal component scores, then I can explain more variance. So in other words, I get these factor scores that represent personality, academic achievement, and intellectual ability, and can use them all in my model because they will not be highly related. And that's probably not going to make a lot of sense when it's presented to you in narrative form, but when you see this play out using our statistical software package, I think it becomes a little bit clearer. At least I hope it does. The reduction methods that we're going to study, principal component analysis and factor analysis, they're often confused. The one thing they share is they're both reduction methods. The thing they don't share is what they actually seek to do. Principal component analysis, um, I would say, creates a new variable based on a set of observable variables. And we create this new variable such that they're linearly independent, and they're some linear combination, usually based on some weighted mean. So if I have like 20 measurable observed variables, I may lump the first 5 together and create PCA1. I may create the next 6 together and create PCA2. So I'm taking the observed variables and collapsing them down into components because that set of that set of measurable outcomes kind of lumped together in some way. Factor analysis is just the opposite. Factor analysis seeks to uh, create take measurable scores and kind of map them onto a factor where a factor represents a latent, non-measurable, non-observable outcome. So again, what's a component? Well, it takes measurable stuff and creates measurable stuff, observed stuff. Factor analysis takes uh, uh, items, clumps them together, and then names the factor based on some summary of the items. Again, both are reduction methods. Something I did once, ran a factor analysis on a final exam. I used to, one particular semester, we had a lot, and one thing to find out about this, the sample size required is at least 300. It works a lot better with 1,000. But I had a sample size one semester. We had a lot of Stat 1150. It's our intro statistics course at Shawnee. And we gave, I think, a 30 question final exam. Well, if you think about teaching undergraduate statistics, there are quote unquote components that are naturally in the instruction, in the design of the course. First thing we do is we look at descriptive statistics, and then we get into probability. Then we get into to inference, and then sometimes we get into correlation and regression as a separate component. Well, I ran factor analysis on the final scores, and it was really interesting that the first factor that emerged was almost every single test item that I had selected to test the first component. So these things just naturally highly correlated, which tells me that if students understood, they may not get the entire uh, set of questions correct, but they understood the components as they were presented as instructional units. And I found that really interesting, kind of scary in a way. I don't know why, but how the factors loaded on the design of the instructional units. Uh, so anyway, PCA seeks to reduce the number of variables, analyzes the variance, and you're going to see all this stuff as we develop it mathematically. What's a factor? Again, it's thought of something that's not directly measured, but something that's similar in the pattern of responses of the observed variables. And the example I'll give there, I think, is a really good one. Questions on income, education, occupation are things that we could gather on a group of students or subjects. And socioeconomic status could be something that is considered a factor of those three observed variables. So factor analysis, we have two parts. We are just going to use the exploratory, or we're just going to examine exploratory factor analysis. In other words, we're going to go in and summarize the data and examine groups that are highly correlated. Confirmatory factor analysis actually allows you to test a theory. Where that would come into play, and I want this to be on your radar. Anytime in ed research that you use a survey, a survey will start out with like well, let's not use N, let's just say K questions, 30 questions. We'll run a factor analysis on it and see what the factor structure looks like. Does it end up in 2 factors or 3 factors or 4 factors? So if we create our own data set, then we may just want to summarize the data and explore the factor structure. Well, that obviously falls under exploratory factor analysis. But let's say that we're examining a factor structure from a previous study, and we want to test if our sample follows the same proportion, or gets the same, ends up in the same factor structure, then we could test that using confirmatory factor analysis. Again, in this class, the only thing that I present is exploratory factor analysis, because that's the process that most students would use on their master's thesis project. Limitations, no way to test your solution. You could examine a factor structure and end up with a 4-factor model. I could do factor structure and end up with a 3-factor structure. We're both right. We've just described it differently. There's no p-value that says my factor structure is actually better than yours. We look at a scree plot and examine these things like eigenvalues, and we try to make a cut where we've explained the highest percentage of variance without adding another factor. So again, this will become clear as you see it on play. Infinite number of rotations, so the final decision depends on the researcher's interpretation, just as I said. And we need a really large sample size. Usually we talk about 300 being the cutoff. I've actually found one of my doctoral advisors actually had studied factor analysis in depth for years. Really, really smart guy out of South Africa. One of the smartest guys that I've had the pleasure working with. And he found that really this process is quote unquote unreliable until we get up to about 1,000 subjects. So just keep that in mind. But again, typically most research projects, if we can get a sample size 300 or larger, it's okay to proceed with this process. Well, speaking of, I didn't realize I put this screen there, but 50 poor, 100 poor, 200, yeah. If you come to me and you want to run a factor analysis on 50 students, I'm not going to let you. There's other things we can do that I'll help you. But we need at least 300. Again, that's just really repeating things that I've already presented to you. Now, again, I want to, so, again, some more information about principal component analysis. So the number of components equal the number of observed variables. The first component has the most variance, second, and so on and so forth. I'll demonstrate that with a tea kettle at the end of the video, which kind of makes how you rotate something to get the best picture of the variation in an object. Non-mathematical, but I think it kind of helps sink in the idea of rotations. So we'll get to that in just a second. But at this point, I want you to pump the brakes and just understand again how important it is to understand the difference between something that is measurable and observed and something that is a latent underlying uh, uh, characteristic, if you will. For example, get on a little bit of a tangent here, so we may not get this in 12 or 15 minutes. If we're analyzing intelligence, for example, one of my best friends is just convinced that his wife is the most intelligent human being that ever lived, and she's clearly a bright person, but she's extremely well read, and she retains what she reads, and she has an excellent recall, and she's very quick. So, if she's doing Jeopardy, she's killing it because she has very quick recall, and she reads a lot and retains a lot, right? So I think that is one component to intelligence. But I wouldn't want to get caught on a deserted island with her because I don't think she has that level, that type of intelligence to figure out and problem solve, to survive and to get off the island. So I don't think she has the practical, creative component of intelligence, but she's again very well read. Well, to me, intelligence is kind of like there's an analytical component. There's I don't know. I think there's a creative component, and I think there's a practical problem-solving component that comes together to create this unobserved, latent variable that we call intelligence. Um, again, a lot of talk about grit these days. As I'm creating this video, I currently have 4 students examining grit as predictors of success in a college class, some online, some face to face. If you think about grit, I think of things like conscientiousness, courage, uh, persistence, resilience, uh, just a down deep desire to excel, kind of a level of perfection. Describes one of my daughters to a T. Self-esteem. If I think about self-esteem, there's self-confidence, a sense of belonging, a sense of identity. I don't know. I'm sure there's other components. I'm not an expert on self-esteem by any stretch. I'll tell you another one. My wife is a school psychologist. Uh, just like personality types. If you're going to measure like a personality type, you can't just give a single question, an observed measurement to a student and say, okay, what kind of personality do you have? We would want to dive in. I think there's something called a Myers-Briggs test. I've heard my wife talk about that. That it's an instrument that dives in and asks different questions to examine whether someone is like an introvert or extrovert, whether shoot, I forget what the other things are. Oh, there's like if you when you're kind of viewing the world outside you, are you a do you perceive things or do you judge things? Anyway, I'm getting in a in a field here that I know nothing about, as you can tell. But again, pump the brakes. Do you understand the difference between an observed variable and this underlying characteristic that we call a latent variable? So hugely important. All right, rotation. It's used after the principal component analysis to maximize the high correlations. We'll study on Varimax, and you'll learn more about that as I think you need to learn more about that. So, uh, well, our eyesight just went crazy, didn't it? I found this video on YouTube and I thought it was really pretty creative. It giving us a visual on what really goes on with principal component analysis in terms of rotation. And we get into it, I like it because it doesn't list things like eigenvalues and covariances, eigenvectors. So they say if you're taking a picture of a teapot, how would you take the picture to capture the most information about the teapot? And I think most people would agree that the top right one would provide the most information. Now, how do you find that? Well, if we start with just some random picture, we could start rotating the picture until we get to a point where the variance components are the highest. Now, what I mean by variance component is let's go from left to right. If I go from left to right, I have a variance component. I'll just call it the horizontal variance component. And if I go from top to bottom, I have a vertical. Notice that the vertical distance and the horizontal distance are greater than this picture right here. Hence, I'm seeing more of the teapot or tea kettle. What is that? Well, whatever. So most people would choose the top, and why? Well, for reasons that I just explained. So in other words, we rotate the object around its center to find the best orientation that extends the most in the up and down vectors. Same thing if we do just look at points. Now imagine these points could be anywhere in the space. We move them down to where they fit uh, around the origin. Okay, now if we look at the most variation, which I'm going to identify as the first principal component, the first variation goes from the point all the way to the left. I'll try to circle it to make a point, and all the way to the right. So that variation, which is given by the line PC1, is the most variation that I observe. The second most variation I observe is the vertical component, which would actually run from this point all the way up to probably this point. Could be extended into 3 cells or 3 dimensions if we want. We would just look at a dimension, well, we've all seen 3-dimension plots. All right, so that's all I've got. I hope that helps a little bit, and I hope I kept this thing, this instructional video around 15 minutes. If not, sorry. All right, take care.